Good morning, and thank you for having joined this presentation within the CIRPe 2020. This work is titled Robust Optimization of Manufacturing Systems Flexibility, and it is a joint work between myself, Chiara Magnanini, and Professor Tullio Tolio from Politecnico di Milano, and our colleague from the National Research Council of Italy, Walter Terkaj. First of all, the agenda for this presentation. I will first introduce the work and the motivations, especially the industrial context and the related state of the art. Then I will talk about the methodology presented in this work. Therefore, I will focus on the performance evaluation model and on the optimization problem which constitutes the overall approach. And then I will apply the methodology presented to a real industrial case and show some numerical results. I will conclude this presentation with hints about some future research. Nowadays, frequent production changeovers lead to the need of manufacturing systems to be endowed with flexibility and reconfiguration capabilities in order to be robust to changes in the production scenario. Especially, highly automated lines are characterized by fast, repeatable operations, which make this type of lines very efficient, but also very sensitive to any occurring disruptive event in one stage, which then propagates its effect along the stages. Moreover, recent technological developments push the design of serial lines, taking advantage of modularity to enable easy reconfiguration of the system. Therefore, a modern serial line may undergo several configuration optimization decisions along its life cycle, and also its performance evaluation change according to the configuration. Configuration decisions include a wide variety of aspects, such as buffer capacity and allocation, machine capability selection, machine cycle time balancing, to mention some of them, but also sensor allocation in order to understand where critical machines are, or for data gathering for applications of Industry 4.0, and so on. Each decision may represent a constraint for the future and limit the company competitiveness. In this context, volume flexibility may guarantee to the company a certain degree of flexibility in proactively addressing production changes. However, in order to assess the volume flexibility, the system performance should be evaluated in an accurate way, and the configuration decisions optimized efficiently. Therefore, here it is when we come to the objective of this work. The aim of this work is to present an analytical methodology to support the optimization of manufacturing systems configuration. The overall methodology integrates an analytical stochastic model for the performance evaluation of manufacturing systems into a mixed integer linear programming problem by means of performance linearization. How has been this topic treated in literature? The optimization of manufacturing systems aims at the optimization of system performance with respect to a user-defined objective function, usually a cost function, depending on specific decision variables. Normally, the productivity of the system configuration, like the throughput, is among the main system performance measures of interest. So, however, we may include also other. The decision variables may include a wide range of decisions, from the buffer capacity to the stage cycle time to the machine capability in terms of reliability and maintainability, represented in the table by the mean time to repair and the mean time to failure. It must be noted that all the system performance measures, again, as the throughput or also the average work in progress or the system lead time, do not vary linearly with respect to the change in system parameters. Performance evaluation tools, such as analytical models or discrete event simulation, estimate the performance of possible system configuration by taking into account the stochastic dynamics and propagation of effects. and therefore they can efficiently support the companies in the configuration phase. Optimization methods for supporting decisions are usually loosely coupled with performance evaluation models. Why? Because in general, optimization is carried out through iterative procedures by keeping the evaluation module independent from the optimization module and having the two modules exchanging iteratively input and output. This is why optimization methods based on linear programming normally consider the performance evaluation of the system as linear with respect to the varying parameters, hence introducing much approximation in the real performance metrics. On the other hand, if accurate performance evaluation models are used, black box heuristics are usually preferred, thus leading to near optimal or suboptimal solutions. These can jeopardize the final configuration decision and therefore the investment done by the company. That is why we classified the analyzed state-of-the-art papers, here are only some of them, according to the decision variables to see how many types of actions are covered by that approach, by the configuration evaluation method, and the optimization method. For instance, whether the model is based on the real dynamics of the system, as in simulation models or approximate analytical models and so on, or queuing network, or the configuration is based on simplified linear performance. Then the optimization method, whether it is based on genetic algorithm or heuristics, or some smarter way of including the knowledge of configuration evaluation into the optimization. And that is why we extended the table by adding the relation between the performance evaluation and optimization. If we come to the presented work, what we do is to integrate an analytical performance evaluation tool into an optimization framework, into a mixed integer linear programming problem, by means of linearization of the performance. Therefore, first of all, we will explain how the algorithm works. In particular, the algorithm starts with the initialization and setting of the target throughput. The iterative loop of the algorithm consists of the optimization of the configuration, including an estimate of the throughput, thanks to an approximation based on linear constraints. The candidate configuration obtained as a result of the optimization problem is given as input to the performance evaluation model for an accurate estimation of the throughput. The algorithm proceeds iteratively until convergence, which means until when the throughput estimated by the performance evaluation is greater or equal to the target throughput, while considering a tolerance, a small tolerance. If convergence is not reached, then first-order derivatives are extracted from the performance evaluation model and used to generate a constraint, which is called a throughput cut, linearizing the performance that is added to the optimization problem. We will see now why we are talking about an analytical performance evaluation problem and how the linearization of the performance occurs. The performance evaluation model is an approximate analytical model based on Markovian modeling. Each machine is characterized by production rate M, failure rate, and repair rate modeled by means of Markov chains of continuous time, discrete state Markov chains. Each buffer has finite capacity equal to N. There are no restrictions on the distributions of the line, of the failure, of the repair probabilities, and so on. A linear system of differential equations is solved by a numerical algorithm in order to evaluate the system performance in terms of throughput, average buffer level, and steady-state probabilities. The linear system is obtained by means of decomposition equations, which are based on the system dynamics. The system dynamics included the propagation of effect, which means blocking and starvation phenomena along the stages. The model has been already presented in other works and proved itself to be accurate with respect to real cases. The advantage of using an analytical model is that the explicit relation between input parameters and output performance can be obtained. In fact, based on this model, the first derivatives of the system throughput with respect to the existing parameters can be derived. Why are we interested in first-order derivative? Because performance measures such as system throughput do not depend linearly on the system parameters. Therefore, the derivatives are used to write the first-order approximation of the throughput with respect to the system parameters. For instance, let us consider the throughput variation with respect to the buffer capacity n, which is shown in figure. If the first derivative of the throughput with respect to the buffer capacity is known in a certain point, the tangent line to a given point can be written by means of the equation in the slide. Therefore, the linear approximation of the throughput curve increases the accuracy for each tangent line added to the set, if we increase the number of points where the tangent lines is written. What we obtained in the end is the combination of hyperplanes approximating the response curve of the throughput with respect to the given parameters. How the first-order derivatives are used and how the linearization of performance is used in the optimization problem. The optimization problem is formulated as a mixed integer linear problem, a MILP. The goal is to minimize the overall cost given by the purchase of machines and buffer slots with respectively xn and x, while satisfying the target throughput. An upper bound for the throughput can be calculated thanks to a preliminary analysis of the problem, since we have the detailed modeling of the serial line. Then, one machine type must be chosen for each production stage among the feasible ones. Given the choice of machine time, it is possible to calculate the actual mean time to failure for each production stage, since in this work we have been able to include only performance measures depending on buffer capacity and mean time to failure. Finally, the optimization problem includes a constraint representing the throughput cut that is added after each iteration based on the linearization of the throughput, which is shown in figure in yellow as throughput cut. Let's see now an application of the proposed framework for optimization. The approach has been used to evaluate the optimal improvement strategy in a real manufacturing line. The company is an Italian manufacturer that produces drawers for personalized kitchens of a well-known Swedish company. The sides of the drawers are assembled by the production line shown in figure, and it has a high level of automation, as we can see from the video. 4 stages can be identified in the line, and linear guide rails serve as buffers in the line where the capacity is given by the total length. Therefore, the modularity of the line is also exploited by moving the machine modules along the guide rails in order to allocate more or less buffer capacity between machine stages. Now, this company wanted to test a predictive maintenance strategy in order to select the right combination of station components for which the predictive maintenance strategy should be implemented. The complete set of possible actions is provided in the table. In total, 5 machine configurations can be tested, which includes the base case and the 4 improvement actions. Each action has a different impact on the mean time to failure. However, the overall impact on the system performance, such as the throughput, is not known in advance. In this case, a predictive maintenance strategy is tested in order, therefore, to see on how many components it does worth implementing this strategy. At the same time, buffer capacity can be changed, so we want also to include in the optimization the change in the buffer capacity, which, as we said before, can be achieved by moving the station modules on the guide rails. Currently, the throughput of this line is 6.6 parts per minute, but the target throughput to be achieved after the optimization, or that the company would like to achieve, is plus 30%, so which means approximately 30%, which means 9 parts per minute. The optimization algorithm has provided the solution in 10 iterations with a total optimization time very low of not even some seconds. A current study on the optimization time, optimization time is currently under development. The optimal solution consists of implementing actions A3 on the first station and action A4 on station M2, which means that 3 components should be the objective of the predictive maintenance strategy on the first station, and 4 components should be predictively maintained on station M2. Why? Because these has been highlighted, these 2 stations have been highlighted as the most critical ones from the performance point of view. At the same time, it is optimal to reduce the buffer capacity of all the buffers to be equal to 3 parts. Among all possible combinations, 10 iterations means that 10 configurations have been evaluated. It is interesting to notice from the 2 graphs that not all actions tested increase the throughput while increasing the costs. Also, it is interesting to notice how the optimization approach explores the solution space. So the solution space is explored without a gradient-based approach, which is usual of the heuristics used in this type of problems. Therefore, the change in the value of parameters to be tested is rather big. And the comparison with other search methods is currently under development in order to highlight the advantages of using the proposed approach. In conclusion, a novel integrated approach for the optimization of stochastic manufacturing systems has been presented, and the decision support tool for optimizing system configurations is coupled with an analytical performance evaluation model in order to provide fast and robust solutions. With respect to other approaches, the proposed methodology exploits the knowledge of the system dynamics for exploring the solution space, and future research will involve the generalization of the approach to include any type of actions with effect on all the system parameters. It could be also interesting to optimize not only the system reconfiguration, but also the management in terms and operations in terms of control policies. Stochastic-based approaches as 2-stage or scenario-based programming could support even more in solving problems related to future uncertainty. And for this, I would like to thank you for the attention, and please do not hesitate to ask questions. Thank you very much.